Okay, we're in Chapter 17, Introduction to Solid-State Devices. What happens is that I have atoms. The atoms have shells that have electrons in them. When I have an atom like copper that has one extra electron in its outer shell, it becomes a conductor. When I have an atom like helium whose outer shell is filled with two, it becomes an insulator. When I have something that's in between, halfway between, it becomes a semiconductor. So semiconductors can go both ways. They can either have an electron that's free floating around, or they could act as an insulator and not allow electrons to move around. So in the case of our favorite semiconductors, carbon, silicon, and germanium, they all have 4 electrons in their outer shell. Now, we know that that's a pretty simplistic way to look at things, because as we go on in physics, we get away from the idea of having electrons in shells, and electrons are in clouds around the electron, and there's a probability of them being someplace. So this is a first order approximations of how the atom works, but the explanation works for semiconductors as we use them, so that's why we stay with it. There's an energy difference between each of the bands that are of electrons around the atom. As I get closer to the atom, I'm going to have more energy that I can release if I go further away, and it has to do with Coulombs Law that says, let's see, it says something. The force is 2 charges, Q1, Q2 over the radius between them squared times some constant. This constant is a very big number. It's like 10 to the 10th, 9 times 10 to the 9th, which is almost 10 to the 10th. So when I have an atom that is, and I'm talking about radiuses that are extremely small, and then I go and I square that extremely small. So if I have 0.1 and I square it, then I get 0.01. 1 over 0.01 would be 100. So this guy here, when I get down to the nano centimeter type things, nanometers, as close as I am to that plus and minus of inside my atom, those are big forces that we're talking about, even though they're very small charges. And what allows us to have the science we do. So as I get further away, my energy becomes less, and I can free an electron up more easily as I get further away from the center of the nucleus of an atom. We call them conductive bands. So the conductive band, the valence band, is the last set of electrons around the nucleus of an atom. I wouldn't be able to get the electrons that are really close in the first couple bands, because they just have too much energy to get there. Unless I have some science fiction film where I have solid electron, for example. So there's some science fiction things out there that allows me to do that. But in reality, I don't think that would work very well. So a semiconductor works because sometimes its valence electrons can be released, and sometimes it can't, depending on other things going on. So when I put these silicones together, I have covalent bonding. I'm bonding in the last ring of electrons. So I expect to have 8, 1, 2, 3, 4, 5, 6, 7, 8, and I do. And they're sharing electrons, and they're hanging out together. And double clicking is not a good idea. And then when I release that electron, when I get rid of it, and I go from a valence bond to a conductive bond, band, I can release electrons from those bands, having a positive charge electron hole, and then they could recombine. I could bring it back in. So if I energize this semiconductor material enough, charged it enough, I could release some of its electrons. I could be conductive in nature. If I didn't, then I would be an insulator. So what we're going to do is we're going to dope the semiconductor. So if I had only silicon atoms in my semiconductor, it's not going to work very much. But if I dope it with aluminum or boron or whatever that guy is, or gallium, arsenic, actinium, bismuth, phosphorus, if I put some impurity in it, then I end up having either 3 electrons that can be free or 5 electrons that can be free, depending on which impurity I put in. So now I can make a diode with gallium, or I can make a diode with arsenic and have different properties of that diode. Not that we know what a diode is yet, but that's beside the point. So I end up putting in, I dope my material, and this would be an N-type. So I have N-type for negative, and I have P-type for positive. So I put in a N-type material, and in so doing I get an excess electron. And that excess electron is what's going to let the charges move. I can have a P-type material, which would be aluminum, and then in a P-type material I have an extra hole, which means I have a positive. The thing's positively charged. Because an atom in and of itself has as many positive charges as negative charges associated with it. If I go get rid of an electron, now that atom becomes positively charged because of the positively charged nucleus. All right, so now if I take my P material and my N material and I bring it together at some junction, what will happen is that they'll attract each other. The P's and the negative charges, the positive and negative charges, are attracting each other, and I end up with a depletion area between them. And it's going to be the size of that depletion area that's going to decide whether or not I can actually pass current or I'm not going to pass current. So the negative charge on the N-type material is causing a positive charge in the depletion area, and the positive charge is causing a negative charge in the depletion area. Okay, if I go and I put a positive charge into the positive side, now I'm going to start moving things in that direction. If I put a positive charge on the negative side, nothing's going to go anywhere. It can't move. So I don't have current flowing in the opposite direction. But I do that by P and N-type material. Now, this is something that we figured out between World War I and World War II. Before then, before we had semiconductor materials, we had vacuum tubes that were doing the exact same thing electronically, but they weren't doing it the same way physically. So I can have a vacuum tube that acts as a modern-day diode does. And I was doing that during World War II. I was doing that during World War I. Between the two world wars, we ended up figuring out that we could have semiconductor material, and by changing the doping and changing the sizing, we could make various components. It wasn't until the Battle of the Bulge that we had 4 layers of this material put together. So in 1944, during the Battle of the Bulge, 1943, during the Battle of the Bulge, no, it was 44. We ended up with proximity switches, RF proximity switches in our artillery and in our anti-aircraft bombs that changed the nature of warfare. So before then, when the artillery would shoot at the infantry, the artillery would hit the ground and blow up. Well, something that hits the ground and blows up, I can dig a foxhole. With a proximity switch, I can set my proximity switch to say, have this shell blow up 20 feet above the ground. Well, now with a shell blowing up 20 feet above the ground, I'm raining shrapnel into the foxholes. The Germans didn't like that. They didn't think that was fair, and the war soon ended. Probably not because of what they were thinking, but for other reasons. Prior to the proximity switch, we were using 10,000 rounds to knock down one plane, one Japanese plane. With the proximity switch, it only took 2,000. That was another issue that the Japanese had. So when we're outside of Iwo Jima, defending it from the kamikaze attacks, we had proximity switches on our weapons, which changed the effectiveness of the kamikaze attacks. If we had the same effectiveness of our anti-aircraft weapons that we did at the beginning of the war, when the Japanese came out, we would have been 1/5 as effective knocking down their planes. That would have meant we had many more footages of their kamikaze planes hitting us instead of being blown out of the sky. That would have been an interesting part of the battle. We still would have taken Japan. We probably would have had to use more than the 2 nukes that we did. In order to get, it would have been more difficult to get close enough. That would be the issue. Okay, so I have some junction between my P and the N material, and I have a depletion layer between them, and I have a potential barrier between them caused by that depletion area. So I can have, I can bias. This is now 2 things together. P material, N material makes that a diode. So this is a diode. The diode is either forward biased, so it's forward biased if I have positive charge, a positive voltage on the positive side, ground on the negative. It's forward biased if I have a negative voltage on the negative side and the positive guy is biased. Either way, I'd be forward biased. Depending on what I make it out of, the voltage I need to push past the depletion area to get current moving would be 0.7 volts in a silicone diode and would be 0.3 volts in a germanium diode. Now, the germanium diodes are more expensive by about a factor of 10, so we don't use them very often just because they're more expensive. But it really doesn't matter one way or the other, right? Expenses. So when the first Voyager was sent out, the one that went to Jupiter and then Saturn and then Uranus and Neptune, that guy, and is still going, he went with 3 computers. And as long as 2 of the 3 computers agreed on some command, then they would execute that command. They were made not of silicone technology, not of germanium technology, but a ruby on ruby technology. And it turns out a ruby on ruby doping of the rubies allows me to be extremely non-sensitive to radiation. And out in outer space, a solar flare puts out all kinds of radiation. They made it to the first 2 places with all 3 computers working. They left the solar system with only 1 computer working of the 3 they had on board. So they ended up having to shut down the other 2 because they weren't working right. But that was just because of the atmosphere they're in. Now they're outside the solar system. They're past the orbit of Pluto, and they're keeping on going. And maybe a couple million years from now, they'll end up someplace where somebody of intelligence will see them. Or we will go and get them ourselves. That'd probably be more likely. Our technology will change, and we'll go get those first Voyagers before they get anyplace else. Okay, so forward biased of the PN junction of the diode occurs at 0.7 volts for a silicon diode, 0.3 volts for a germanium diode. And if I have a light emitting diode, they're normally about twice that amount. So about 1.4 volts to turn on a light emitting diode. Okay, reverse biased. So okay, what do we notice in this picture? Anything important? Where is my there it is. All right, now how am I going to get, oh, there he is. All right. Somehow my thing that was on top wasn't on top. That's an interesting noise. Anyway, what it's showing here is current moving from the negative side to the positive side, and we're an electron flow type of people, and so really we have to go and redraw the drawing so that the current flows the other way. So my current really flows in that direction. The positive guys are moving that way. And I turn the battery around so my current is flowing that way. I'm going in that direction. Okay, so this is reverse biased. In reverse bias, I close the switch. I'm trying to get the current, the positive current, to flow past the positive person, so I'm going to have no current flowing. I'm going to have a depletion layer with the switch off. I turn the battery around. I close the switch. Now my positive guy is flowing into the negative guy. I'm getting a big depletion area, and I have reverse biasing of my diode. So a normal diode looks like this. If I'm positive on that side and negative on that side, I have current flowing. If I turn my diode around, I'm positive on that side, negative on that side, no current. I am reverse biased. But the transparencies I have are all for electron flow. The author didn't make a second set of transparencies. So for a PN junction, I'm biased, forward biased if I'm positive on the positive side and I've ground my negative, or I'm negative on my negative side and I've ground my positive. I have a minimum depletion area. I have minimum resistance, and I have maximum current flowing when I'm forward biased. When I'm reverse biased, I have positive voltage on the N material, I'm grounded on the P material, or I'm negative on the P material, positive on the N material. In either case, I'm reverse biased. I have a maximum depletion area, a maximum resistance of the device, and a minimum amount of current flowing. And for our first thought about what minimum means, we think of it as zero. There's no current flowing. Now there's always going to be some current flowing, right? So there's this wall there and that wall over there. There is going to be some current flowing between those two walls through the air. It's going to be nanoamps, it's going to be picoamps, it's going to be some really small amount. And if I don't have the right meter, I won't be able to measure it. We call it zero, right? That'd be perfectly okay. So here we go. This is our IEEE now gets in the act and comes up with a diode. A diode has an anode and a cathode. The words anode and cathode are saved from our tube technology. So when we had tubes, we had anodes and cathodes. When we have diodes, we brought those same words with us. We think of the anode as an A for add, which is a positive sign. We think of the cathode as not being the anode, it has to be negative. Okay, so that's how we remember the difference between an anode and a cathode. Because it's an IEEE guy, an IEEE symbol. An IEEE symbol is for positive current flow. I have a funnel, my positives flowing into the tunnel and continuing on. If I have some positive on the negative side, then it's not going to flow. A diode has two conductors, two different things. It has N material and P material. So now I look at my diode and I see that I am forward biased. Well, that's convenient, isn't it? Well, I guess we just have to live with it. So I see I'm forward biased. My current's flowing that way. I see that I'm forward biased again. My current is flowing this way. So I've grounded the positive side. I have negative voltage on the negative side. I have current flowing. My path of current is through my grounds because I have to have a complete circular path of current. I look at this guy, I'm positive, I'm reverse biased. I can spell bias, and there's no current flowing. I'm reverse biased. There's no current flowing. Zero current is going through my meter. If I have a really good meter that can get down to nanoamps, yeah, I'm going to see a little current, but that's none. That's no current. Ideal diode characteristics would act as a switch. I'm either open or I'm closed. I have, in the open position, I have infinite resistance. There's zero current flowing, and it drops the applied voltage. All the applied voltage gets dropped across the device. In the forward bias condition, I'm a closed switch. There is absolutely no resistance. There's no voltage across the terminal. So that's my first cut about what a diode does. An ideal diode is either on or off. And in general, that's how I think about them, and that's how I use them. So I have a situation where I'm either on or I'm off. In the real world, there's a forward voltage that has to be applied before it turns on. We call that knee voltage, VK for knee, and it's 0.7 for a silicone diode. Again, as an ideal diode, we'd say at 0.7 it turns on and it's all the way on. So even though we're turning it on at a little bit higher voltage, we're going to, for an ideal diode, on is on, off is off, there's nothing in between. We look at practical characteristics of the diode, and we see that I have some diode I have to change the direction of current, and that's what I'm doing. Okay, so, well, okay, so I want the voltage across R1, and I say it's going to be 4.3 volts. I'm measuring it. It's 4.3 volts. I find my current is going to be 4.3 milliamps. Well, if it's 1 kilo ohm, Ohm's law says that V is equal to IR. So current had better be the voltage divided by the current. I'm measuring 4.3 volts divided by 1K. So that's why I'm seeing 4.3 milliamps. I could, if I wanted to, I could say I know what the forward voltage is, I know what the source is, I know that I'm going to have a 0.7 drop across the diode. If I have 5 volts, a 0.7 drop across the diode, that means I only have 3.4 volts across my resistor. We'd call the resistor a current limiting resistor. It's saving the diode from burning up. Okay, so an ideal diode would have an infinite amount of resistance going through it. That would not be good. So if in fact my real diode characteristic looks like that, have 0.7, and I've got 0.7 across it, I'm going to have maximum current that's going to burn out, right? So something has to give there so that I'm not burning out my diode, and what's giving is that I have a current limiting resistor thrown in the circuit so that it limits the current through the diode, and I don't burn it up. All right, now there is going to be a peak reverse voltage on a diode. And in this case it's showing a minus 100 volts, but when I make that diode, there's some reverse peak voltage that if I go above, I'm going to break the diode, and it's going to burn out, and it's going to turn into a piece of melted thing that's going to sit there and allow current to flow. So at some point, I'm going to force the semiconductor to conduct. So the air in this room, if I had 1,000,000 volts on that wall and minus 1,000,000 on that wall, the air in this room would in fact conduct. And there'd be large bolts of current going through the room, and they'd be very dramatic. And if we were standing in the way, they would be going through us. Okay, so if I have enough reverse voltage on anything, I'm going to break it. Okay, diodes are just little things. Minus 100 volts is going to be all it's going to take. I have an average forward current. That's the maximum allowable DC current to have this thing last for 100 years, which is sort of what I'd want for it to last forever and ever. And that's why I would put in a current limiting resistor to keep the maximum current flowing through the diode in the range that I'd like it to be. There's a maximum power distribution that's allowed by the diode. There's it's going to heat up naturally. It will dissipate heat naturally. Clearly, we don't want it to melt. So there's going to be some maximum power it's going to be allowed to have before it melts. There's going to be some bulk resistance of the material. The P-type and the N-type material have some resistance associated with them. That resistance is why there's a 0.7 volt drop across it before it turns on. And this bulk resistance is going to affect the operating range of the diode. So I have some diode. It has a battery in it that's 0.7 volts. It has some current flowing across the bulk resistance, and that's going to give me my forward voltage that's going to have to be used to turn this thing on. All right, now we're looking at what a true diode would look like. So a true diode isn't doing what the ideal guy is. So in the forward direction, I'm not a straight line. I come up a little bit. I still have a knee voltage at 0.7 where I start taking off, but now I'm taking off and I'm increasing the voltage across this as I run current. I have some maximum current, 100 milliamps in this case, so I have some maximum forward operating. So I have some forward operating region that I can operate in. I'm going to be, we call this a characteristic curve. I'm going to be someplace on that characteristic curve. In your lab work for the class, you'll be taking data to make those characteristics curves. When I reverse bias the diode, I have some region where I have some back leakage current, and then I have some maximum voltage where I break. So I've reversed, this is my reverse region. I'm in the breakdown region. The diode is failing. It is never going to work again. Okay, so if I allow myself to get past that maximum reverse voltage, I have destroyed my diode. Now diodes, I buy them for 7 cents a piece. Okay, for one of you guys to replace something, getting paid the normal $150 an hour you expect to get paid, it costs several $100s to repair a diode, right? Now, if we're only paying you the normal $15 that we're going to pay you because we're too cheap, then I can replace diodes for cheaper than that, right? But after benefits, it's going to be $150, or even if we pay only 15, right? With Obamacare the way it is. No? Anyway, so this is a true diode characteristic curve. It still has a knee. It has a forward operating region. It has some part where it's not passing a whole lot of current. You can reverse bias it. There'll be some reverse current, not very much. And then, but when it breaks, it breaks. So we have milliamps on the top. We have microamps in the negative direction. That's microamps are not very many, but this guy goes to infinity very quickly and destroys itself. Reverse current. A very small amount of minority current passes through the diode when it is reverse biased. So 1,000th of what we would expect it to be if it's forward biased, but a very small amount does go through, and we would go and we would have to know that value. We have two independent currents going on. We have a reverse saturation current, and then we have a surface leakage current. Okay, so reverse saturation current is the breakdown one. The surface leakage current is until we get there. The diode also has a capacitive component associated with it. So because there's an insulator involved and conductors involved, that's sort of like two plates of a capacitor, and the diode's going to have a capacitive component associated with it as well. Normally it's something so small that we don't worry about it. The temperature effects on the diode. If I go and change the operating temperature of the room, or the temperature of the diode for that matter, because it's heating up, I change the operating characteristic of the diode. So my knee gets moved over, my voltages and my currents are different between 100 degrees centigrade and 25 degrees centigrade. And if I do something and throw this diode, a regular diode, up into outer space where the temperatures could be considerably more different, then that characteristic curve would change more. And that's why they had to use, they couldn't use, you can't use just regular diodes in outer space and expect them to work. And the military, of course, couldn't put up with this either. They want their equipment to go 125 down to minus 125 without any problems. And so they would have to have special diodes too to make them work. Okay, with that, we're to 17.7, which is as far as we need to go. So that means it's time to work some problems. Anybody have any particular problems they'd like to have worked? Looks like we'll start with number 8. Determine the values of the voltage across diode 1, the voltage across resistor 1, and the total current in figure 44A. Alright, so we got 44A, 6 volts, one lousy resistor, 2.2 k ohms, and a diode. D1. Okay, so we want this is R1. So we want the voltage across R1, the voltage across D1, and the total current in the circuit. Anybody have an answer for any of those? Okay, so I look at the circuit, the first thing I notice is the diode is reverse biased, right? Reverse biased means no current. No current means total current is 0 amps. Okay, so if I have 0 amps going through R1, what's the voltage across R1? Yeah, V is equal to IR, so if I is 0, it doesn't matter what R was, the voltage across the resistor is 1. What's the voltage across the diode? Well, so that's correct, 6 volts. Guys, Kirchhoff's law says the summation of the voltages on a loop has to be 0. So if I go up 6, I go down nothing, I'm going to have to go down 6 more, right? So we could call it minus 6 volts, that would be okay, but we couldn't call it 0 volts. Want me to move that a little bit? See if I can make that look better. Minus 6 volts. Depending on how I put my voltmeter. But if I go up 6, down 6, then I'm 0, like I'm supposed to be. Okay, we happy with that? Okay, well, let's see. We'll put it in multisim, see what multisim says. That's always fun. See if it says 0. Yes, I agree. That's awful embarrassing, yes. Nothing. Nothing.
Yeah, you. Don't worry, I thought I heard you. Yeah, everybody's sound like 15. Huh? 12.
For the people that choose to sit in the back row.
Yeah.
Okay, picture right. I have R1 saying R1 D. So the only thing I don't have are the other guys to say the right thing. Okay, let's turn it on. What do we got? And I'm supposed to have 6 volts. Okay, 0.8 microamps, giving me 1.3 millivolts, giving me 5.999 volts. Close enough to 0, 0, and 6 volts? Yeah, close enough. Is there current flowing through the diode causing this? Or is the current flowing through the resistors, the voltmeters, causing this? Yeah. So if we take our voltmeters and change this to tera ohms on our voltmeters, I bet you that we going to see a better result. There, is that better? So now we have 6 volts showing up there. We have 28 nanovolts showing up across there, and virtually nothing. 0.8 microamps. Is that better? So it would appear that because this is a virtual diode, I would imagine that its characteristics are pretty much ideal. And it's our meters that are causing the change in our numbers, not the diode. And we could, why don't we add another instrument, seeing that we're appear to have enough time to do that. We'll put another amp meter in. Do you think it's connected? I don't know. Okay, so there, that shows what we're talking about. I have 0.8 microamps flowing in the circuit, but only 6 picoamps going through the diode. The rest of that current is flowing through my voltmeters. Pico 10 to the minus 12, so that's basically 0. Okay, happy with that? Number 11 next, or do you want me to do another one before number 11? Determine the values, voltage across D1, D2, R1, R2, I1, and I2 for...
We're doing number 11, right?
That's what I'm doing, number 11.
You got number 1 on the board.
I do? Where? I'm going to go look. I'm looking.
You fixed it.
Looks like 11 to me.
Sorry, only one class.
Yeah. Must,
Alex's head was blocked with the other one.
oh yeah, what happened? Okay, so where were we? 1745A. And so I've got one battery, 10 volts. I've got a resistor, 1.5K. Got another resistor, 1.8K. I got a diode going that way. And I've got a diode going the other way. D1, V1, VR1, R1, R2, D2. Is the picture right? All right, now I look on the left-hand side, I see I'm reverse biased. Okay, so reverse bias means that the current 1 is going to be 0. So I don't have current going that way because I'm reverse biased. Okay, if that current is 0, then the voltage across R1, which is I times R, I current being 0 means that it has to be 0 as well. The voltage across D1 we're going to count as minus 10 volts. So I go up 10, I go down 10, I get 0 in that loop. Okay, so now we're going to look at the other side. I look at the other side and I say I'm forward biased. Forward bias means the voltage across D2 is going to be 0.7 volts. The voltage across R2 is going to be 10 minus that 0.7 volts, which will be 9.3 volts. Total current, the voltage, 9.3 volts, divided by the resistance, R2, 1.8K. At that point, we would break out our calculator and put some numbers in it. So 9.3 divided by 1800. And I'd come up with 5.2 milliamps. Okay, so that would be the answers for the problem to the degree of knowledge that we have. Now, if we knew what diode it was, D1 and D2, then we could go look in the spec sheet and find out what the reverse current was, that 1 microamp, and we could come up with another set of numbers. But if we only have 2 significant digits, we'd end up with the same answer, because that would be in the grass. Okay, so that was 11. Looking at 14. Want me to do that in multi-sub to see what the numbers are, or do you trust me? You trust me?
Trust you.
Well, you don't trust me. I know that. You keep an eye on me. How's that? Okay, 14 is next. 14. What is the minimum required peak reverse voltage rating for the diode shown in 1746A? Okay, so we've got a AC power supply, and we have 100 volts peak on that power supply, and we've got a 10K resistor, and we've got a diode sitting just like that. Okay, and what we're worried about is not the forward, but the reversed bias guy. So what we're worried about is what that voltage, what the rating for that voltage should be. Alright, so my power supply goes up, my power supply goes down. My power supply goes up, my power supply goes down. The peak voltage is 100 volts, so I go up to 100, I go down to minus 100. Okay, so the first thought would be voltage reverse peak. Is that what it is? Minimum required peak reverse voltage. Peak reverse voltage should be minus 100 volts. Okay, and if that's what we thought, then we are not thinking as engineers. We're thinking as something else, as little sisters. There we go. I like that. Okay, how many think that minus 100 volts is the right answer? All right, now, whenever you have a minimum requirement, you always have a design margin. Okay, what should the design margin be? Anybody remember from last semester what our design margins usually were? You don't. Does anybody? No, no one does. So normally we add a 20% design margin. So our thinking answer would be minus 120 volts, would be the thoughtful response would be minus 120 volts because we throw in the design margin. The non-thinking response would be minus 100 volts, which I'd probably have to count correct because I'd have to make sure you guys pass, right? Yeah, something like that. But the engineering response would be minus 120 volts because I have to have a design margin in everything. Okay, so that was 14. 22. A silicon diode has a bulk resistance of that. At what value of forward current will the value of F, the forward thing, equal 0.8? All right. 22. So did I get the 22 right? All right, so I've got...
Those look like fancy ones to me.
I got 20 ohms. Now the picture I recall is that I've got some battery and some bulk resistance inside my diode, right? So that's the model we're using to do the equation. So let's go back and see if we can find that model. Okay, there it is. So I have some voltage B, bulk. Okay, so and the equation says VF is equal to VB plus IF RB. That's what the equation says. And it also goes on to say that this guy is 0.7 volts. All right, so we want 0.8 volts. 0.8 volts to equal 0.7 volts plus IF times 20 ohms. And now we reduced the words, which are totally, completely confusing and irrelevant to us on a one-to-one basis, into one equation, one unknown. All right, so that being the case, I subtract 0.7 from both sides. 0.1 volt divided by 20 ohms equals IF. Hey, where's my calculator? I found it. 0.1 divided by 20. looks like I have 5 milliamps. Okay, so that was 22. Yeah, were we lucky on that one? Yeah, we were. We were lucky on that one because we remembered from our transparencies the model that they wanted us to use, and from that model we found the right spot in the book to use it. 28. Refer to figure 1749, which is a page away. 1749. A circuit has an average forward current of 3.6 amps and a 170 volt peak source. Which diode has the minimum acceptable ratings for the circuit? Okay, number 28. Okay, so I have 3.6 amps is my forward current that I need. And my voltage reverse voltage 170 voltage peak. And I'd probably take both of those and multiply them times 1.2 so that I'd have a design margin before I looked on the other page. Now, you could probably get away with not doing that, but some of us in the room do have master's degrees in EE, and that would require us to do it. But you guys are only training to be technicians, so chances are you can get away with it. Let's say if we have this. Now we're going to look at the diode. So what diode does that for us? So we'd probably go with a 200 volts in the reverse direction, and we need 3.6 amps. So that looks like our only choice is MR752 for a diode. Do we have another choice on the bottom? 200. Those guys are huge amperages, so looks like we only have one choice. And even if we went with just 170 volts, 3.6, we'd come up with the same answer, right? Because we wouldn't pick the 3 amp guy for a 3.6 amp guy. All right, 28. Looking at number 30. Would somebody read problem number 30 out loud for me? Yes, please.
Where'd the 1.2 come from on that?
Design margin plus 20%. So if I go plus 20%, that means I'm multiplying times 1.2. 100% plus another 20%. So that's where that came from. Anyway, back to number 30. Would somebody be so kind as to read problem 30 to me? Oh, you gotta have a book too. All right, problem number 30. All right, what do you say?
Is that our diode spec sheets?
Good enough. All right. Clearly, we can't do problem number 30, right? Because Steve just said a word, Zener, that we haven't said yet, right? So that means we're up to 17.7 and we're done.
Thank you.